previous lecture I started design of controller for the multi-cycle data path for the MIPS processor. We will complete that design, and I'll also take another style of design called microprogram design. In the overall scheme, we are here. We are going to concentrate on microprogram control and also finish this control part design. We will also look at two different alternatives of design, PLA and ROM. So we will look at the implementation of controller, which has two parts. One part produces the control signals, other part decides the next control state, and each of these could be either implemented by a PLA or a ROM, as we will discuss later. And then finally we will talk about microprogram control design. So this was the data path we arrived at for multi-cycle approach. The picture shows all the control signals which are useful for controlling various components, and this is the overall flow chart indicating how control state changes from cycle to cycle and what action is taken in each control state. We have identified groups of control signals which need to be controlled together to do some basic operation, which we call as micro operation. So all micro operations were identified, and the pattern of control signals required to make them effective have also been identified. Some symbolic names were assigned to these micro operations, and then in brief we replace all the assignments and all the transfers by names of these micro operations, and also we label all the states. So now this is the most crucial part of the design. After this, the implementation starts. So we try to capture all this by two tables. One table describes the control signals for each control state. Okay. So for different groups of control signals, we are indicating what micro operation they are supposed to perform, and each of these corresponds to some pattern of control signals. So if you substitute that, if you replace each micro operation by the pattern of control signals from one of these tables, okay, what we get is this. Okay, each micro operation has been replaced by a pattern of ones and zeros, and also there are X's indicating don't care wherever appropriate. So now this basically is like a truth table description, and all that is required is that we encode these control states also in binary form, which you see here, that each state can be encoded in 4 bits since there are 10 states. This forms the truth table where the part shown in black is the input and part shown in green is the output. Okay, so basically it's a 4 input, and this I think numbers up to 20. So 20 output and 4 input is what this table describes. So this can be implemented by a PLA, as we have discussed earlier for single cycle design. This PLA will have 4 input coming from the control state, and 4 groups of control signals, group of 4, group of 5, another 5 and 6. So altogether 20 signals which go to the data path. The other table is what describes the next state given the present state and which instruction or instruction group we are talking of. So we have the same 10 states, and instructions have been grouped as usual: R class, SW, LW, BEQ and J, and for each row and column combination we are describing what is the next state. So this is these two tables together are basically capturing this flow chart or state transition diagram. This table can also be replaced by a binary equivalent, where we substitute code for each of the control state, and also we specify the opcode value for various instructions. So after having replaced the control state codes in this table, we get this. On this column also we replace, okay, all the states are replaced by their codes, and opcodes are also put there. So now it describes the truth table with a group of 4 inputs here and group of 6 inputs there. So this table is defining 4 bits of 4 outputs, and there are 4 plus 6 10 inputs. So we can have it described by implemented by a PLA, but before that I am showing another way of looking at it. So here this is a more compact representation, because here you notice a lot of sparsity. All right. So we can, instead of having a 2D table, I am showing it as a one-dimensional table where all input combinations are listed vertically. So the current state and instruction combination, but we don't have 2 raised to power 10 entries here, although there are 10 bits of input, because there are lots of X's or don't cares. So all the relevant combinations are captured. So for CS0, irrespective of what the other input is, the next state is CS1, and so on. For all these, the next is a fixed state. So same table is rewritten in a different form, okay, and once again you can replace the state numbers, state labels by their code to get this, right. So now you can look at it in a more conventional form, a truth table where you have first 2 columns represent the input, so together 10-bit input and 4-bit output. So here is a PLA which will implement this 4 bits of control state and 6 bits of opcode to produce next state, which has 4 bits. Now, how do you what is the overall picture of the controller? We have these 2 PLAs implementing those 2 specific tables, but all put together we also need register which holds the state value, and at every clock this value will change as per these tables. So here is the state register, okay, it's a 4-bit register which contains the current control state, and this drives both the PLAs. This PLA is generating the control signals going to the data path, and this PLA is also looking at the opcode and deciding what is the next state. Okay. So one could have thought of this as a single combination circuit with total of 10 inputs and 24 outputs, but that is possible, and it will be correct, but that will be much more complex than these 2 smaller PLAs put together. So at this point I want to bring in another alternative to PLA, again another general purpose component which can be derived directly from a truth table. So suppose you have a truth table, fully expanded truth table with n inputs corresponding to 2 raised to power n rows, and it defines m outputs. Okay. This can be implemented essentially by putting this entire pattern of outputs in a memory. So in particular we are talking of read-only memory, the kind of memory we use for instructions, where you are not modifying the contents, you give an address as input and out comes the data. So these n inputs which you want to apply to the combination circuit you are designing, you apply as address to the ROM, and you read out contents of the addressed word. So it effectively works out as an n input and m output combination circuit. The definition of the function which this implements is directly given by the output columns of the truth table. Okay. So each row of the output part corresponds to one word in this memory. Okay. Now how does this alternative compare with the PLA? All right. The difference is in terms of size, whereas a memory like this will have 2 raised to power n words, each of m bits. Okay, so total number of bits is m multiplied by 2 raised to power n. On the other hand, a PLA which is implementing an n input m output circuit will have an AND plane and OR plane. So there will be rows running for all the inputs, okay, in rows corresponding to true logic and false logic. There will be vertical lines which will implement AND gates, and there will be rows here, one corresponding to each output, which will form the OR function of some of the product terms. So, what is the size? What governs the size of this? Okay, size is governed by these three factors. One is n, other is m, and the third is the number of number of vertical lines you have to run. Each vertical line here corresponds to a product term, or you can alternatively say a row of the truth table. Okay, so it corresponds to, suppose there are k terms in the truth table, but remember that truth table here could be not in a fully expanded form, it could be in compact form with lots of don't cares. So, if there are k terms, then the total size would be, which you can see as area of, roughly area of this rectangle, it will be proportional to k, that is this dimension, multiplied by n plus m, because this n plane accommodates rows corresponding to n inputs, and the OR plane corresponds to m rows corresponding to the output. Okay, so the height of this would be proportional to n plus m, and the width is proportional to k. In general, k is likely to be much smaller than 2 raised to power n, and that's what makes a PLA much more economic and compact as compared to ROM. So, if your truth table have lot of sparsity, if there are lots of don't care, then you can compact whole thing in the form of a PLA. Otherwise, ROM is a reasonable alternative. So, to illustrate this point of compact representation, suppose in your truth table there was a term like this 0x110x, and for this the output is 1010. So, in PLA you can take it as it is, it will correspond, it will contribute 1 to that k. Okay. Whereas in for a ROM you need to define output for each combination exhaustively, right. So, such a term will actually show up as 4 terms, where you take all possible values for these x's. You substitute 0 0 0 1 1 0 1 1, you get 4 possibilities, and for each of these you need to ensure that the same output is there, because with any input the output must be defined here. All we are saying here is that 4 terms are grouped here. Okay. So, irrespective the value of second input and the last input, if this is the pattern 0 1 1 0 here, then this should be the output. So, in a fully expanded truth table, this will correspond to 4 terms, and this is just one simple illustration. On the whole, you could see an example of a let us say, if you were to implement this by a ROM. Okay. This will require 4 plus 6, which is 10 inputs. That means 2 raised to power 10 or 1024 words in the memory. Each word will be 4 bits, and total number of words will be 1024. But in PLA, you will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 terms. Okay, so k will be 14 here, right. Each of these will correspond to product term. For example, what you are saying here is that if this is 0, 0, 0, 1, 1, 0, irrespective of any value of this, and 0, 1, 1 here, that should be the output. Okay. And so a term like this expands to 2 terms in case of a ROM. Things like this will expand into 2 raised to power 6 or 64 terms, and so on. So, that is why PLA representation will be much more compact here. Okay. Now, what is this other style of control design which I mentioned, microprogram control? Here we try to view the controller as something which is a small program. Okay, is it something like a small computer trying to control the data path. So, if you look at this, for example, you could think of this as a program flow chart. All right. So, if you take that view, why not think of a controller as a small computer which executes a simple program, and that program has basic operations which are micro operations, and it all it does, it generates control signals for the data path. Okay, so this is a program which does nothing else. It does not deal with manipulating data in the main memory, does not deal with the register file and so on. All it does is that it goes through steps. Each step involves generating some control signals for the data path. So with that view, we think of a memory here containing microprogram, and all we are doing is we are reading out words of this memory. Okay. So you might think that now I am again talking of memory, although I have just mentioned some disadvantage of a memory based design, but there are differences you will notice. So imagine a memory which contains a microprogram. What this microprogram is nothing but each word contains a bit pattern which needs to be applied as control signals to the data path. Okay. So those signals are not generated by circuit, they are simply read out from this memory. All right, you step through different words, and each word generates appropriate control signals for the data path. So this will have the word will have 20 bits plus a few more bits that I am going to describe in a moment. So these 20 bits will simply go as inputs to the data path and control it as required. Now the question which now remains is that how do we sequence through different words of this microprogram. Okay, so sometime we will need to go sequentially, word after another. Sometime we may need to jump from one point to the other point. So here is a little arrangement to make sure that the right address is presented to this memory, so that the correct word is read out in every clock cycle. And how we generate this address is by another box which we are calling as microsequencer. So microsequencer is ensuring that right address is put in this register, which we are calling as micro PC or microprogram counter. So it is the counterpart of PC as we saw in the main program. Okay, in main program PC is stepping through memory locations which contain the instructions. Here it is micro PC, which is just a 4-bit register. It steps through different words of this microprogram memory to ensure that the right signals are generated at the right time. To ensure that this works correctly, each micro instruction will say something about where the next micro instruction is. Okay, so each micro instruction may say that either we follow sequentially in the address or we branch to something else. So that information somehow will be communicated by a few bits of the instruction, and this microsequencer will look at these bits. It will look at the current value of the microprogram counter, and if necessary look at some signals coming from the data path. So in this case it is the opcode bits. Now you might be wondering that we are now talking of a box which has these 4 inputs plus these 6 inputs, 10 and a few more here. So isn't this going to be very complex? The answer is no, because you would notice that quite often you would simply go to the next instruction or the next micro instruction or the next word. So it is only in those cases where we are not doing so, the logic has to do something else. But otherwise a simple incrementer or adder will take care of bulk of the task, and we need some more logic to take care of those conditions where you are branching off. So in our flow chart, what all was happening, let us see. So we are going sequentially. For example, here, here, here. The points where we are branching is here. This is one point we are branching, another point we are branching, and these are few points where we are restarting the whole thing. So we need to take care of these. these are the 4 possibilities that you follow a simple sequence. In one of the instructions, in one of the steps, we are branching to CS2 or CS4 or CS8 or CS9. That's one branch point. We call it dispatch 1. So, in microprogram terminology, a multi-way branch like this is called dispatch. There is another point where we are branching to either CS5 or CS6. So, let us call that dispatch 2, and there are several states where we are going to CS0. So, let us call that reset. So, now that few bits in the instruction which I was talking of here, it needs to specify one of these possibilities. So, the possibilities are sequence, dispatch 1, dispatch 2 and reset. These are the four possibilities we have identified. This is a specific case. Okay. In general, when you are talking of more complex design, these possibilities could be larger, but in our case a 2-bit field here will be sufficient to tell what we want to do as far as determining the next address is concerned. So, the microsequencer needs to work with these 4 possibilities, and it will be selected by 2 bits coming from the microprogram, which we call as sequence control. So, this will select either current MUPC microprogram counter +1 or 0, or an address which we have called as dispatch 1 or dispatch 2. So, these are small boxes which are looking at the opcode and generating the correct address. Okay. So, once again you can think of these as small tables. Depending upon the opcode value, you want to pick up one of those 4 possible addresses. Here, depending upon opcode, you want to pick up one of the 2 addresses. So, these could be small ROMs or small PLAs. So, we leave that here. The main point is that there are a very small number of ways in which you need to determine the next address, and a few bits in the microprogram will control this multiplexer. So, now how does the microprogram look like? We have a microprogram containing 10 instructions. So, this is a very low level program, lower than the assembly language program which we studied initially in the course, and very simple primitive operations are being done. Each line here I have written so that each line represents one micro instruction or one word in the microprogram memory. Incidentally, microprogram memory is also called control store. So, the first instruction I have labeled where you fetch, do PC increment, and the sequence control is that you go in normal sequence. In the second one, we are doing this and doing dispatch 1. Here we do dispatch 2, and here again example of sequence, and then rest are reset. So, there are labels I have put. When you do dispatch 1, you are branching to one of these labels beginning with 1A, 1B, 1C, 1D. There is a choice of these. In dispatch 2, there is a choice of 2A or 2B. Okay. So, this is a microprogram written in a symbolic form, and once we understand what each of these symbol is, a micro assembler can translate this into the contents which will go into the control store or the microprogram memory, right. There are variations in the way you structure your microprogram. There are 2 styles. One is called horizontal microprogramming and other is vertical. What the approach we have followed is what is actually horizontal microprogramming, where you allow many operations to be done concurrently. Whatever the data path can support, you have a provision of doing many micro operations together within the same instruction. So, there is a high degree of concurrency. Vertical would mean low degree. That means you try to do only one thing at a time. So, fetching an instruction and PC incrementing there would be done in 2 different instructions. All right. The idea there is to conserve the space. Here, as you have seen that altogether the space we require is just 10 words, and each word having 22 bits. So, it is not too much of space and we will not worry. But in past many processes have been designed which have been very complex, and microprograms run through thousands of words. Okay. apart from the concurrency of micro operation, there is also a question of how you encode each micro operation. So, the way we have encoded was that we should be able to directly get the control signals out of the pattern of bits. But since the number of patterns which are really utilized is much less than the log of the number of bits, the number of patterns in general could be 2 raised power the number of bits, but the number of useful patterns is much less, and we can use a more compact encoding. So, a vertical approach would try to do a more compact encoding, and idea here is to have low memory requirement, whereas in horizontal microprogramming the idea is that you do not lose performance. But on the whole, the microprogrammed approach versus non-microprogrammed, which in contrast is called hardwired approach or finite state machine based approach. What are the pros and cons? The specific advantages of microcoded approach is that it is often easy to write it like a program. The definition of control can be written in a flowchart like form, and then you can easily capture in the form of a program. And one could work with design of the architecture and design of microprogram independently. In terms of performance, however, there are issues. In past it was thought that processor could be one chip which will have data path, but the control could be moved out into a separate memory chip which is ROM, and you could change that. Okay. So that suppose you want to make a change in your processor design, want to add few instructions, you could simply modify just contents of this memory, and rest could remain same. So in fact several times the families of processor were designed like this, that you would have different microprogram implementation, although the data path may be same. Also there were attempts like emulation of one architecture by other. That means you have a processor which was designed maybe with a fixed architecture in mind, but you can have a microprogrammed hardware which can implement one or more architectures. So that is the process is called emulation. So you try to emulate. Emulation is something like simulation in a microprogram. Okay, you try to simulate the effect of another set of instructions, and microprogram would have access to all the internal registers, temporary registers. For example, in our design we have register A and B. Okay, a person working at assembly level will not know that there are registers A and B, but one who is working at microprogram level could make access to those registers if it is required for implementing something. But penalty of all that is that this approach makes it slower, because memories would tend to be slower than much slower than the PLAs, for example, which is the other alternative. And so now this approach is no longer popular, partly because there is a lot of performance penalty, and partly because you have now tools where even those TDS finite state machine design are not to be done by hand. Okay, so you could leave, for example, at a point like this, and the tools will take care of the rest. Okay, so coming up to this point is not difficult, and this was considered as an advantage of microprogram earlier. That is, from here one could by hand or by an assembler fill up those bits in the memory. But tools can design very efficient finite state machine or hardwired controllers, starting from this kind of description. So now, looking at all these possibilities we have talked of, we have multiple options at various levels, various stages in the process of design. At the initial representation level, you can draw a finite state machine diagram, or you can write as a program, microprogram. At sequencing control level, you could have either explicit next state function coming out of a PLA or memory, or you could have microprogram counter plus dispatch ROMs. Okay, and these arrows show that you can start with this, go to this alternative or that alternative at the next level. Similarly, you can start with this and go either way. At the next level, you have logic, where you can write as logic equations or you can write as truth tables. And finally, at implementation level, you can have PLA or read-only memory. So you have many, you have multiple options at each level, and technically all combinations you can start here, go to this, come to this, and finally implement like that. So all those are possible. Okay, to summarize, we completed the design of the controller which we started last time, and we saw that we require two PLAs. One takes care of generating the control signals for the data path, and second generates the next state for the control. We saw ROM as an alternative to PLA, but there is a problem of large size, and this difference could be very significant in many cases. And thirdly, we looked at microprogrammed approach to control, where the three main things are: there is a microprogram memory which contains so-called micro instructions. There is a microprogram counter which drives this memory, and there is a micro sequencer which determines contents of the microprogram counter. I'll stop with this. Thank you.